Yeah, I've since been corrected that I technically may have seen a movie that had Nicolas Cage in it, but it was possibly over a decade ago. So my memory is not that good. So I'm Melanie Cebula. I'm a software engineer specializing in cloud infrastructure, and I'm here today to talk about trends in cloud-native efficiency and performance. So first, some very important disclaimers. This talk contains my personal views. It is not about my employer, nor is it about my employer's views. Also, this talk contains predictions and speculations which could be wrong. So this is just my space to come up with trends that I see that I would like to share with you. Cool. So today's agenda, we have 30 minutes. I'm going to give an overview of the space, then I'm going to talk about the latest hardware in the cloud, particularly with processors, memory, disk, pricing, and instance sizing. Then I'm going to talk a little bit about the OS kernel and JVM, latest updates there. Going to switch to schedulers and containers, perf tools, and then networking in the cloud, particularly a little deep dive on service mesh and new technologies like eBPF. Okay, so first some definitions. Who here knows what cloud native is? Okay, some people. Who here has workloads in the cloud? Okay, so cloud native means technologies that were built to run on the cloud. So common cloud native technologies include containers, service meshes, microservices, schedulers like Kubernetes, and common principles include immutable infrastructure and declarative APIs. Usually these technologies are part of continuous integration and continuous delivery, which is just a fancy way of saying the automated shipping of code, and DevOps, which involves engineers shipping and being on call for their own applications. Often these technologies are vendor agnostic, open source, and can run in any cloud environment. And as we'll see, these technologies influence the hardware and software that they run on. So that's cloud native. What is performance and efficiency? Performance work involves measuring and improving metrics such as CPU or memory usage, throughput and latency of systems and services under load. Efficiency work involves improving the overhead of compute, such as improving binpacking or autoscaling behavior with the goal of saving on cost. So you can use this efficiency or performance lens to look at any part of the stack, from the hardware at the bottom through to the software at the top. So cloud native basically changes everything about this paradigm. These days, a lot of us are now running compute as a distributed system with containerized multi-tenant workloads, which has a huge impact on how you approach performance and efficiency work. So with that in mind, I'm going to talk about the latest hardware in the cloud and what that means for you. Cool. So starting with processors, memory, and disk. Every year, all cloud providers update their offerings to include the next generation of hardware. 3 of the big processor vendors are Intel, AMD, and recently, Ampere. So very recently, Google announced that they'll be the first cloud provider to run Intel Xeon Sapphire Rapids with a custom Intel IPU as part of their system-on-chip design. We also have the next generation of AMD EPYC designs, and both Google and Microsoft are offering Ampere Ultra instances with Ampere 1 on the horizon. AWS also has their own ARM-based processor, the Graviton instances. So this is the very low-level part, and now I'm going to bring it up a level for what that actually means. So all of these processors highlight several very interesting trends. The first trend is customization in the cloud. So we're seeing the golden age of the custom cloud processor. All of these cloud providers are heavily investing in their systems on chip or SoC design, and so for each component, they can either build or buy that component, the CPU, the TPU, or the IPU. So for example, AWS iterated on their own ARM-based processor, which is Graviton 3. And other cloud vendors, such as Google and Microsoft, are using Ampere Ultra's cloud-native processors. So they actually even have like cloud-native processor in the name. So cloud-native workloads are actually changing the hardware. And recently, Google also has their latest iteration with a custom IPU. So we're seeing far more customization for more components in the cloud than ever before. The second trend is the rise of ARM. So all major cloud vendors now have an ARM64-based processor in their offerings. This is related to the SoC trend, but ARM specifically is taking off due to the licensing terms of ARM, the company, which allows for a lot of customization, as well as the underlying energy efficient ARM64 design. So if you use the cloud, you may have noticed that they all made big splashy announcements about these new instances. But if you didn't notice, I'm here to kind of fill you in that this is just part of another trend that I see, which is that processors are now targeting efficiency more than before. So we have these cloud-specific optimizations, which is their secret sauce that they will not share with us. We're using custom chips for cloud native, and they're optimized for actually what we're running in the cloud. So more than ever, we have multi-tenant services. That's just a fancy way to say more than one application on a piece of hardware. We have schedulers, we're running containers, and these workloads have differing needs from traditional workloads. So for example, we're spending a lot more time with microservices calling other workloads and waiting for a response. So we're seeing a real shift towards efficiency as a top concern, and maybe even more important than performance for some workloads. So ARM is one part of this because it's an energy efficient design. The architecture basically has different cores doing different tasks. And Intel also has its new processor similarly has performance cores and efficiency cores that can either target the performance ones target the heavier tasks, the efficient ones target background tasks. So I think we're going to see more focus on this energy efficiency in the future. Okay, so if you're using the cloud, that means we're in the era of more CPU choices, and you can actually select your hardware for your workloads based on price, performance, efficiency, and also now architecture. Okay, that's enough about processors. Let's talk about memory. Again, a lot of our workloads these days are not actually CPU bound. So many microservices are actually memory IO bound, and they use a lot of bandwidth. So other advancements like DDR5 is a big deal, which is advertising 50% bandwidth. And some of the latest processors have it. So I just listed some of those here. They're either GA or they're coming out this year or next year. Finally, I'm going to talk a little bit about storage. We see that NVMe 2.0 has improved throughput and IOPS, and PCIe 5.0 has improved speed and bandwidth. These are coming soon. Finally, block storage has improved a lot and become much more stable over the years actually. So together, this means that you, or probably your engineers, might actually be able to reevaluate the best storage solution for your workloads based on their needs. Okay, so talked about processors, memory, and storage, and I want to talk a little bit about pricing. So shout out to the previous talk on saving cloud costs. That was the culture piece. I'm talking a little bit more about some of the technical and strategy piece. So another topic here is this idea of pricing versus availability guarantees. So all cloud providers have similar tiers of pricing that are based on these basic categories. On demand or pay as you go. This is convenient. You won't pay for more than what you're using, but you're paying a premium for that convenience. This is often the default, so this might be what you're using. Reserve or pay up front and save. This is a way to save money if you pay up front. But it can be challenging to determine how much you should actually reserve. If you reserve too much, you may have wasted reserve instances. If you reserve too little, you might still be paying a lot in on-demand costs. And this is because usage for many customers is spiky. So it can be hard to get the balance right between these two pricing tiers. However, there is another pricing model that has emerged in the last few years, which is spot, or what I like to call save on extra capacity, but no guarantees. Basically, the cloud providers themselves have excess capacity and don't want it to go to waste either. So this excess capacity is offered at a significantly reduced price, but they can be claimed and reserved at any time, unlike other instances. So you are in no way guaranteed this capacity. It can go away very quickly, sometimes within a minute, and you may not get it back. So also pricing depends on what is actually in the market. So with these three pricing tiers, we have three different ways to get compute based on pricing versus availability guarantees. And I made this nice little chart to just summarize where they fall on the graph. Cool. So the overall trend I've seen in the past few years is that all cloud providers now have a solution for their excess capacity. And this is actually starting to look like market dynamics are at play. For example, I looked it up, and Azure has a setting where you can set your maximum price and evict if the cost goes over the price. So you're actually bidding for your compute. And I think this is a neat idea when demand is low and supply is high. But I also think it'll be interesting to see when the reverse situation plays out, particularly when demand is high and supply is low. Maybe surge pricing for hardware? So to go back and update this trend, I think we're seeing even more choices amongst price, performance, and availability. So what are you optimizing for? Absolute performance, absolute price, or absolute availability? More likely in most companies, you're going to pay for performance and availability where you really need it. And then, if you're running an important business, you probably need to save on costs with efficiency where you don't need those guarantees. Okay, finally, when it comes to hardware, cloud native really changes how I think about instance sizing. So historically, you have a virtual machine. This is kind of when you go into the console and you launch a new instance. It has resources such as CPU and memory, and you vertically scale the machine as you need to take up more resources. In the cloud, this usually means you go up in instance size, so you get one larger instance. But with the cloud, you can also horizontally scale. You just add another virtual machine. You keep adding them as you need to scale. There are obvious limits on vertical scaling. For example, if you're already on the largest instance size, you can't go up one more size. But larger instances change in other ways. For example, you might be vertically scaling from a single socket box to a 2-socket box and paying a NUMA performance penalty. This is sort of a hidden cost when you go up between certain instance sizes. So the traditional performance engineer perspective is, hey, why pay it? If we have to pay a penalty for larger sizes, what if we just use 2 single-socket boxes that are smaller instead of one bigger 2-socket instant box? So we can actually horizontally scale instead. But when we're running a scheduler in multi-tenant workloads, there's also significant per-instance overhead. So if the per-instance overhead is high enough, you actually might want to vertically scale as much as you can because you're paying that cost for every additional instance. The overhead for 2 combined is higher than the overhead for 1 instance. So in this case, it might be reasonable to look into minimizing overhead, vertically scaling up until this penalty, and then horizontally scaling out. And there's some workloads where this penalty is just a drop in the bucket. Okay. Actually, who here runs on Kubernetes or with a scheduler? Okay, good. You can also look at Kubernetes cluster overhead. So we actually have significant scheduling overhead, which is the resources used per cluster by scheduling logic. Not to mention operational overhead that you or your infrastructure engineers might be subjected to. So you can also vertically scale each cluster until you hit the maximum number of instances and horizontally scale by adding a whole other cluster. Multi-tenancy in clusters actually makes us zoom out from these individual instance sizes and think about this entire cluster and series of clusters, almost like a galaxy instead of the planets in the galaxy. So now we care about the resource of individual pods running on our nodes, running in our clusters. So it's all gotten quite a bit more complex. And this is a really big shift. Before we had maybe one instance, and we're running that one workload on the instance, we're scaling out the instances for the workload, and we just need to optimize that instance for that one workload. But now we have multiple tenants per instance, and they all have potentially radically different needs. So now we have new problems facing us, including resource contention, scheduling challenges, and bin packing. So since we're talking about instance sizes, I'll talk about a basic bin packing problem that I have seen in the wild. So when it comes to the pod itself, this is just talking a bit about vertical scaling. You can increase the memory and CPU per pod, or you can horizontally scale the number of pods with something called horizontal pod autoscaler. But now that we have to scale pods, that's separate from scaling the infrastructure the pods run on. Okay, so let's take a node that can fit 2 pods on it. So the node is just an instance or virtual machine. I call it Kubernetes node because I'm coming from a Kubernetes background. So this node has 32 gigs of memory and 16 CPUs available for all of its tenants, and our tenants are Kubernetes pods. So in this example, I have 2 pods, and they each take 16 gigs and 4 CPUs. our node is fully booked up because it doesn't have any more memory. So we can't schedule another workload that takes 0 memory. But it's actually only using 50% of its available CPU. So if we scale down the node size to 8 CPU, we can actually now fully utilize the node, save on costs, save on performance. Obviously, schedulers try to bin pack to solve this problem, but you could easily be underutilized across your entire fleet if you have common CPU memory requests across your workloads and a common instance size in your cluster. So this is something to be aware of. Okay, so finally, all these trends in hardware demonstrate that we have new requirements with more options for custom resources and architecture. And we have a lot we can optimize on with price, performance, availability, and sizing. Okay, moving on from hardware, next I'm going to talk about some of the latest trends in the OS, kernel, and JVM. So similar to the hardware layer, the cloud provides cloud-specific operating systems, although these are heavily based on open source OSs with some custom optimizations. So examples include Amazon Linux for AWS and Google's container-optimized OS for Google. So cloud providers also offer open source OSs such as Ubuntu and Debian, but this is an important shift towards these cloud-customized operating systems. And just goes to show to highlight the trend that the cloud is optimizing each layer in this infrastructure. So speaking of the container OS, though, there's a lot of changes happening in the industry that I find really interesting. So who here has used Docker before? Okay, or yeah, heard of it. So historically, Docker runs a full operating system, and over time, container optimizations around efficiency and security have emerged. So many containers these days are slimmer, they install less languages. Oh no. How's this? Yay! They install less languages and packages, and these trends have continued, and now we're seeing a concept called distroless, which basically means it only runs an application and the application's runtime dependencies. This is more performant and more secure. However, this also means you don't have shell access and there's no package managers. So if your developers expect to be able to SSH in or exec into a container and run anything, they're out of luck. So with this trend of distroless, which is no shell access, and container hardening, which is no more running as root, and combine that with the fact with some of our performance and debugging tools are not container aware in the first place, we have a massive challenge when it comes to profiling and debugging with containers. So we have to evolve how we debug and profile our applications to keep up with these efficiency and security wins. Kubernetes actually has an answer for this, and it's ephemeral containers. Ephemeral containers are a special type of container that runs temporarily in an existing pod to run user-initiated actions, such as troubleshooting or profiling. This is all pretty early in the ecosystem, but directionally where it's going. I also briefly want to talk about some kernel improvements. 5.10 has several new features and performance improvements, optimizations for new hardware, BPF improvements. Multipath TCP is interesting, but actually I read a research paper on it, and they said in practice it doesn't help in the cloud, so you can just ignore that one probably. PSI, or pressure stall information, which I'll talk more about when I get to containers. And then some I/O wins, such as IOU-ring, which is being integrated into some Java libraries. And that could be a performance win for I/O-bound workloads. Okay, bring it up to the newer kernel versions. So 5.15 is the new standard for the latest cloud OSs, with continued hardware and I/O improvements. 5.19 has more hardware and network improvements. 6.0 has improved NUMA balancing and behavior for two different situations. One, reduced capacity with its load balancing behavior, and two, spare capacity with CPU idle behavior. And it also improves core scheduling. Okay, also, just quickly, some Java improvements. Java 11, we had ZGC show up, and other Java garbage collector improvements. Java 15, ZGC became production ready. Java 17, more improvements, particularly to both of the garbage collectors. The important takeaway is that many applications simply perform much better just after upgrading to these versions. So upgrading your Java version can make very significant improvements to the efficiency and performance of your application and the cost for it to run. There have been more Java versions, 18 and 19, but they're pretty light on these kinds of changes. Okay, let's talk about trends with schedulers and containers. The big change is cgroup v2. Containers are implemented with cgroups, and cgroups is just a fancy way to say a control group, which is a Linux kernel feature that limits, accounts for, and isolates the resource usage of a collection of processes. With cgroup v2, there are several improvements over v1. So, as I said in the kernel side, PSI, or pressure stall information, identifies and quantifies disruptions caused by all resource crunches, which include CPU, memory, disk, I/O, network, and so on. And this could be a great way to prevent and better avoid catastrophic disruptions such as kills, which I don't know if you guys have run into this with containers, but I certainly have. So additionally, cgroup v2 promises better resource allocation and isolation can be a big issue for shared resources like disk I/O and network. This is known as the noisy neighbor problem, and it's just as it sounds. If you're in a building and you have really loud, noisy neighbors, you're going to be bothered by it. And same way with containers. If you have multiple containers running on a host, one container can actually disrupt the resources of other containers by taking too many resources. So improvements in this space can really help you out with that kind of problem. Okay, I also want to talk a little bit about dockerless. This is another trend that I'm seeing, which is most of what Docker provides can be broken down into different functions, and almost all of them are being replaced with competitive alternatives. This is only possible because of interface specifications such as OCI for container images and CRI for container runtimes. For example, Kubernetes is dropping support for the Docker daemon, but you can happily use containerd or cryo. And new tools are showing up to replace building and running containers such as Podman and Builda. So there's a lot of innovation happening in this space. You can also think of Docker as a front end and a back end. The front end is the Docker file. Who here has edited a Docker file before? Cool. Who here has edited a container with something other than a Docker file? Okay, maybe a small number. So this is a new idea, or new-ish, which is you can change the Docker file format and specify an image definition a different way. And the back end is how the front end is built. So just going to the back end real quick, the Docker now has BuildKit, which replaces the Docker image building, and it's faster and more efficient and more secure. The front end, which is the Docker file, also might change. So today the Docker file is highly coupled, right, with the OS, the architecture, a bunch of packages that you're pulling in. And some folks are replacing these with custom image definitions that are a lot simpler, and they hide all these implementation details from the consumer, and they actually move those into the low-level builders on the back end. Okay. One more trend I'm seeing in this space is that maybe VMs are cool again. An example of this is AWS Firecracker. So the key differentiator between containers and virtual machines is that virtual machines virtualize an entire machine down to the hardware layers. Containers, on the other hand, sit on top of a physical server and its host OS and kernel. So historically, VMs are very heavyweight. They've got a bad rep. They're slow to start up, performance is limited, but they're fully isolated with kernels. But for cloud native, right, when we sort of started talking about using containers, they were really promising because they're lightweight, fast startup time, generally good performance, and some isolation management with cgroups. However, containers have been pushed to their limits at times. For example, not having true isolation, the noisy neighbor problem, which I have been bitten by, and other advancements such as cgroups V2 aim to address that. At the same time, VM technology has advanced a lot in this space. So now VMs have faster startup time, faster performance, and they still have all the benefits of a dedicated kernel, which improves security and resource isolation. So what do we do with that? Well, Kubernetes and schedulers and containers are pretty entrenched in the ecosystem, but the advances in VMs are pretty tempting for some types of workloads or their owners. The question is, can you run VMs with your scheduler, such as Kubernetes? Actually, yes, mostly, kind of. There's a lot of details, and they're like VM-like containers. but there is an open solution for this. So I predict that folks that are running Kubernetes or other schedulers might adopt VM or VM-like support that need better isolation and security guarantees. And it'll all fit nicely in this box. Okay, next up, perf tooling. So who here has seen a flame graph before? Cool. Performance tooling has seen a lot of advancements in the last 10 years or so with flame graphs and things like that. Many engineers are now familiar with this picture. And you can see like what a flame graph is it's like a graph where a portion of CPU time, memory, or whatever resource is being spent. And you can kind of drill down to see where you're spending the most time and diagnose where you're spending too much time. This is great if you can capture the exact right moment where your issue happens. But a lot of times, issues happen, just one pod out of 100 pods has this crazy weird issue, and it happens like 1% of the time. How do you capture that and diagnose that issue? So recent advancements in the last few years include continuous profiling, continuous flame graphs. Some open solutions include Flamescope and Parka. And so I think there's a little bit more here to do here, though, with like automated analysis and regression detection. So right now, developers tend to have to zoom in, find the time spot and like actually debug the thing. But I think outlier detection and automated analysis could really help advance this area of expertise. I'm also seeing I cannot say this word, BPF trace being used more in the wild. This is just a fancy tool that lets you use lower level technology to analyze profile without leaving a significant footprint yourself on the thing you're analyzing. So lots of advancements in this tooling, but so far I actually don't think it's all that user friendly. A lot of developers have to train specifically to use all these tools, and it requires a mishmash of different tooling and going up and down different layers to figure out what's actually going on. So my prediction is that clouds will want to invest heavily in better tooling, if only to reduce their number of support tickets. So I think there will be a tool that allows you to zoom out and drill down across layers. And part of that is because I think the layers and the complexity of our ecosystem has rapidly increased. So now we have the application, it's running in a container, we've got multiple pods per host, and we've got the OS and the kernel and the hardware. And a lot of these bugs that I see actually are like at these layer interface points. And so you have to actually debug quite a few things to get to your issue. All that to say is I think there's more complexity than ever in the cloud, and debugging is more challenging than before. So in addition to be time-consuming and expensive, I think an all-in-one debugging tool, maybe I'm just like making my Christmas wish list, but I think this might be something coming out. Okay, so I have time for one final topic, which is networking in the cloud. So networking is not really my area of expertise, but I must comment that networking in the cloud sure has changed a lot in the last few years. So with containers, we have container networking interfaces, or CNIs. And with microservices, or really just services in general, we have service-to-service communication as a top-level concern. The big change in moving service-to-service communication out of language-specific libraries into proxies, like you might be familiar with Envoy or Istio. Actually, who here uses Envoy? Okay, some people. So these proxies generally live alongside the main container in a sidecar proxy container, and these proxies interact with the control plane to allow communication to take place. So this is service-to-service communication. However, with this model, performance becomes more of a challenge. So now with these proxies, we have to right-size their resource requests, including their CPU and memory. And we can't just do it across the fleet because CPU and memory requests actually change per workload. So it depends on your configuration state, how much traffic you're receiving, the total number of listeners, clusters, and routes that you're sending traffic to. And it's not just service proxies. A lot of share concerns have moved from the application to these sidecar containers. So now we have application pods, each running all their sidecar containers, which adds up to a really significant resource footprint. So with this model, we have to tune each sidecar for performance and efficiency. And I think this is why a lot of infrastructure engineers are excited by some way to get out of this problem, maybe eBPF. So eBPF allows applications to do certain types of work in the kernel. A lot of these shared concerns, which are done in sidecar containers today, could potentially be rewritten in eBPF. This logic could fundamentally change how we configure a network, security, and observability use cases with much better performance. But it's much harder to write and reason about eBPF, so that's why it's not radically taking over the space immediately. But that doesn't mean I don't think there's a trend. I think we're seeing eBPF in some places, like I saw it in some CNI technologies, and so my prediction is we'll continue to see eBPF emerge where performance matters, and if it's not eBPF, I still think there's significant motivation for folks to go and revisit this model and eventually find something that works a little bit better for performance. Okay, so here's my summary of my predictions and trends for cloud native efficiency and performance. Disclaimer, my opinions are my own and they may be wrong. So first, custom cloud hardware. We talked about the rise of systems on chips, ARM, and targeting efficiency in our hardware. The era of CPU choice, including price, performance, availability, sizing, and architecture. We talked about microservices and how they change resource requirements and scaling considerations. And multi-tenancy in general introduces challenges such as resource contention and binpacking efficiency. We talked about how the custom hardware has also reached the OS level. So we have custom cloud operating systems, we have container optimized operating systems, and we have distroless. We talked about cgroups v2 and other changes in the kernel that have resulted in better resource contention and isolation for our containers, which solves the noisy neighbors problem, well, helps solve the noisy neighbors problem. Dockerless trend as well, which talks about replacing different parts of the container runtime, builds, and interface. And also, maybe lightweight VMs are cool again, and might replace or be alongside containers with our scheduling technology. Then I talked a little bit about tooling with continuous profiling and analysis, and my hope for more automation in an all-in-one debugging tool. And finally, I put on my networking hat and talked a little bit about eBPF, or how another model might change networking in the cloud. Cool, that's all I have. If you have any questions, you can come to my office hours or tweet me at Melanie Cebula at Twitter. Thank you.